review today. So that's where we're at. The so my palette is my okay, I can go to this edge and pretty far down the other side. So this will be based on your questions. Hopefully you've had a chance to look through the review sheet. It's one of those extra bonus offerings of instructional methodology. Trying to pull up the review sheet myself here so I can reading what you're asking. So on my, just verify for the good of the public, you guys know how to use like a four-way stop, right? If the light is out. Gosh. You must be the only ones in Colorado Springs area. Took 35 minutes to get, oh, it can't be more, it can't be as much as just about a mile from Mark Scheffel to no, apparently there was an accident that took out lights. It was like at Stetson Hills or something.
Yeah, well, I did see something going on at Stetson Hills.
Where did you see that?
It was at Stetson Hills and Powers.
Okay.
Some guy was turning, T-boned another guy, made a truck fly off the road, hit a power line. And the guy turning also ran into the light post.
Oh, actually, so my alternate route would have been probably equally bad coming from like the 24 and Woodman is where I get off at 24. So alternatives, parallel Stetson Hills kind of parallels Woodman, right, on that little chunk. So that sounds like it wouldn't have been much better at all. So they took out two different traffic lights, and people just like mob, instead of like, let's go one, I am at the front, and so one of us will go and cross the intersection while the other side goes across. Now people would like 3 or 4 cars at the same time, and it was not a pretty sight. All right. And they didn't even tell me they were going to do an accident.
I mean, who are you talking about?
What's that? Okay, we got the review for the exam. Let's start there, and then we can go over to the sample questions. Maybe? Come on. Let's go here. Canvas. There we go. All right, so questions you have. Let's start. Let's kind of go. I'll take whatever questions we've kind of worked your way down from the top of chapter 1. Just the only thing, I'm not going to have you do a proof from the using the pumping lemma, right? But what are the big ideas about the pumping lemma? The big one is recognizing that if your DFA has, if you know the number of states it has, if it has n states and it accepts a string of length n or longer, then it must, two things, what two things can you conclude given just those two facts? Or just that, yeah. Has n states, accepts a string of n or longer. So what are two conclusions that you could draw about that language? Or about that DFA? Let's say about the DFA.
In the length of the
Say it again?
The DFA that takes in the length of the string?
Yeah.
Has to repeat at least once.
One more, please.
Has to repeat once.
Yes. So it has to repeat at least once. Thank you. So there must have been at least one state that was repeated. And it could be any configuration. It wouldn't have to go through every single state or anything, right? It could have had just the first state could have had a loop on itself and been an accept state. So it could have been just as simple as this. Say, and you don't care what else over here, but let's say there are 1, 2, 3, 4 states, and I tell you that this accepts a string, at least one string of length 4, then regardless of how it's configured or anything, right? So we're just trying to get at the kind of underlying how. Did I start the recording? Can I find the, there we go. Yes, I'm recording. Sorry. Okay, so if I just know these two things, as 4 states accepts a string of length 4, I know that number 1, at least one state was repeated, and maybe more, right? I can't conclude anything because I don't know what any of these are doing. But if I had something just, I wouldn't even have to know this. I'm just giving a particular example. But if I say this is a DFA, has 4 states, accepts a string of length 4, then you can conclude two things. One is that the language is infinite. Why would I know that? Well, because maybe the first thing to say is, first conclusion is that at least one state got repeated. And from that, the second conclusion would be that therefore the language must be infinite. Because if you repeat it once, you can repeat any number of times. So it kind of gets to the core idea of what a regular language looks like and what you can conclude about it. So does that make sense? Any question about that? So given just these two, or I can change this, right? If I just say DFA has n states and accepts a string of length, I could say greater than or equal to n. then you can conclude these two things. At least one state had to be repeated on that, and the language is therefore infinite. Makes sense, right? Should be intuitive. Shouldn't be like crazy talk. Oh, if you got in late, I did move the exam to 1 week from today to push it off from the algorithms class immediately preceding this. So that'll separate that. So what that means is we're doing as scheduled. I figured you would be prepared for a review today. So we're doing the review today. That's the only thing I'm going to focus on. And then next time, we will continue into the Turing machine stuff. New material that will not be on Wednesday's exam. So Monday will be new material. Of course, I will answer any questions that came up in your studying over the weekend, but that'll give you I think it can only help. I don't think there are any negatives. If there's something that impacts you that you would like to take the exam earlier, we can talk about working that. But that still means that I will get grades in before Friday. So Friday is the last day to drop. I don't think anybody is in dire straits, but I'll make sure that you have your scores at that point by Thursday, so that if you think you might have to make that pull the ripcord decision, then you'll be able to do that with your scores. So, I'm finishing out what I said. So, given a regular language, be able to give or recognize an example of a pumpable substring that would could be repeated within the thing. So if you were given something like oh, I guess did I do the same thing last time? Let's do something a little more creative. Let me see if I can do something a little more. Okay, so one reasonable. I guess that's chapter 1. So the only thing from the last, I don't expect to give you a question from the last exam or recover that material. So, but I would expect you to be able to kind of recognize the language of a DFA like that to the point of draw a string. What's a string that's in this language, and show a repeatable section of that string. So Q3. So what's a string that's in this language of reasonable length? In this case, you could pick the string A is a valid string that's in the language. and the pumpable part would be everything in the so this is one string that happens to be in the language, and you can show that that is repeatable based on the DFA. Let's see, can we make a regular expression for this? Looks kind of like A star, so I could have 0 or more. B, and let's do it just, this is the same as B plus, right? It requires 1B. The alternative is just to put A star B plus. And then, what else? Is there anything else? A. Now, we want to show, well, okay, let's do it. We can do it this way. Like that. Union with A star. Right, so that's a simple way. All right, so you can get to an accept state just staying here, but if you take a trip down the B path, then you have to have 1B many as you want, followed by an A to get you out here. Is there another way to write that? Basically, you could can't use the A. Oh, you could. Alternatively to this, you could make all of this starred. No, you can't. Can't do that. This is the easiest way. There's probably a more clever way to show it in regular expression form, but what was the other? Given a non-regular language, so that no substring can be pumped in within the first character. So if I gave you something like and said so pumping length is the minimum number of characters which is guaranteed to have a repeatable part. And we know it will vary, but P is never going to be greater than the number of states. It could be a multiple of the number of states, I guess. But we don't care. So the question is, could there be a pumpable or repeatable, same thing, in the first few characters? So given this is the pattern, the first P characters are here. So what I'm really asking is, can you pump in some one or more bees into that part endlessly and still have a string that matches the pattern?
Well, you would have to put in as many bees as well.
Right, which would be beyond the question of what the pumping lemma says. The pumping lemma says you must be able, if it's regular, right? A regular language you could put in within that first P number of characters, you could pump in some substring as many times as you want. Okay. And this gets down to really the definition of regular language versus context-free language. This is not regular, which is kind of immediately recognizable by what the sort of memory requirement involved, that in order to get this matching number of, and it doesn't matter, you could use multiples of P or N, still doesn't work. That in order to match that with that, you really need memory. You can't do it with just a DFA. And so that means it's not regular. And so without going into the whole making a formal proof, just being able to recognize that if I have a pattern like that, I cannot, the pumping lemma would say that I could add, if it were regular, I could, within that first P characters, I could add either single bees or double bees. There's some way that I can add a pumpable section that would still give me a string in the language. And so clearly, you can't change the number of bees here and still have something that's in the language. So the answer is, could there be pumpable substring? No. Number of bees won't match is basically won't match number of Ds.
Oh,
Make sense? Make it that way. So I want you to, and what's the point of wiring doing all this? I want you to be able to recognize that this is not regular and that a DFA could not recognize it, because a DFA is only going to recognize regular languages. And part of the reason for that is it would violate the proof, the formal proof would be that it would violate the pumping lemma. If this were regular, then I could pump in as many bees as I wanted. Since it's not regular, this is the result we get. So there's not going to be, you should be comfortable enough with just those three concepts that are in the review sheet. The DFA has n states and accepts a string of length greater than or equal to n. It must be at least one state was repeated, making it also infinite language. Given a regular language, be able to give or recognize an example of a pumpable substring. So if you're given something like this, one pumpable substring would be, you could put in a bunch of bees here and still have something that's in the language. So when you see it in the regular expression, if you have starred stuff, then you can repeat that. If I had, if the language were like this, requiring pairs of bees be repeated, then you couldn't say a single bee was pumpable, right? You'd have to say, if this were the way it's lined up, you'd have to say the whole 2 bees at a time have to be done in order to be in the language. And then finally, just what we talked about. If I give you a non-regular language, it'll be kind of obvious by, the matching situation. Then clearly you could not just arbitrarily put values in here within the first P something like characters, and still have something that's in the language. All right, so I'll let you guys work your questions. Starting at chapter 2, I'm in the review sheet, so I'll go over to the example questions as well. Before we get done, but if we can work off the review sheet first, that'll work smoothly.
So would BP and then just a C be regular language or no?
Yeah.
Okay.
Yeah, because there's nothing to match here.
Yeah.
If you just had some number of B's, that would be like this. Right?
Okay. Yeah.
Yeah, so that's perfectly good. That's regular. It's always when you have that tricky, you have to match the number of things you saw over here with something you have further down in the string or in the pattern. And there's no way for the poor little DFA to remember stuff. Okay, so you want to have this in mind, right? The CFLs, regular languages, are related in that regular languages are a subset. So that means every regular language, what is also context free, but not every context free language is regular. There is overlap, but they're certainly not identical. Can an NFA be implemented using a PDA? Sure. You just have to, the PDA requires what? On a PDA you have, well, we could turn this into a PDA. PDA has rules that look like character, and then stack, symbol, or don't care, and you push something on. So PDA has this format for the transitions, but one possibility is we just put in an epsilon goes to epsilon, which essentially leaves out the stack operation. Right. So we could just add transitions like this, and effectively we turn this into a PDA that has no use for the stack, and it still work perfectly good. You want to remember, what are the 3 conditions for a PDA to accept? Input string has been used up, so input string is empty. The stack has been rendered empty, which it would never get anything on it using this, so it would necessarily be empty. And third one is that you get to the accept state ultimately. So, so that means even though a PDA is what, more powerful or less powerful in what it can accept over a DFA? Yeah, more powerful in the sense that it accepts a broader range of languages. In fact, a PDA will accept everything in here, in the CFL, which includes all the regular languages as well. So it's kind of a, you could make a pretty educated guess that a PDA could accept any regular language. So it must be able to simulate either an NFA or a BFA without problem. So a PDA that we talk about, the PDAs are, you might make note, PDAs that we are talking about are non-deterministic. So that means you could, it would certainly be able to do a deterministic finite automaton. All right, you just, if you have a DFA, you just put the extra stack operations on every single transition. And if it's an NFA, you just do exactly the same thing. And the NFA, by never using the stack, you effectively take that condition out of consideration, right? It's always going to be true that the stack is empty. So we're back to what a NFA requires to accept, which is use up the input and get to an accept state. So there was one true false on exam number 1 that was, let me think how I worded it. Oh, it was like an NFA can accept a string even if there's some extra characters or something in the input that haven't been processed. And that was clearly false. Should have been clearly false. Right, so the NFA, you always have to, if it can get through, I mean, in order to accept, it has to use up all the input and get to an accept state. If it gets somehow to an accept state and there's still leftover characters because you ran, right, an NFA could just have, well, this would be an NFA, say, modification. Yeah, that is a valid NFA. And if I feed it something like that, what would it do? It would start here, go Q0, okay, I did an A, I see an A, so advance. I see an A, so advance. I see a B, so advance. And it can't do anything, can't proceed from there. There's no transitions, and so it'd have to stop. It's not in an accept state. It doesn't really matter if it were in an accept state or not, but it hasn't used up the input. So if it doesn't use up the input, it's not going to accept. Okay, using context-free languages, can you derive a string from a CFG? I guess I should let you guys ask the questions. I'll do this one and then let you ask, or we'll look at the sample question. So, two. All right, so can you derive a string of length 5? Yeah, can you derive a string of length 5 in this using this CFG? Yeah, so we can do what? S goes to A, B. So this is a derivation. This is a, I'll do first a leftmost derivation, which means what? Every opportunity I have to substitute a non-terminal, I pick the leftmost one, which is A in this case. So my target is a string of length 5. So yeah, I can apply, pick another, substitute the left-hand one for a, and now I'll substitute the left-hand one for a C. And then I just need 2 more. I'll substitute the B for the A, C, B, B, and finally put in the D, C, D, B, and that used up all the non-terminals, and so I was able to get to, so this is a derivation of that 5-character string. So what about a rightmost derivation? Is it going to differ in terms of the rules that are used? Answer is no. We're just going to change the sequence, the order in which the rules were applied.
Okay, so you-
I'm sorry, say again? Who I can't tell who's talking when your mask is on.
Yeah, it's a little hard.
Did you have a question or point?
Yeah, so I just had a quick question about, especially when we have things that go through multiple non-terminals. So do you have to go with the leftmost option first when, like, let's say that instead of A going to AA, it went to like AB, and then B went to A or BB.
Okay.
Would you have to, if you wanted to get to C from A, would you have to go A, AB, and then from B go back to A, then go to C? If that makes any sense.
Yeah, so your point is in order, help me out.
Do you mind if I come up there?
No, that's fine. I'm gonna draw it even better.
If you wanted to get to C, but this was replaced with an A here, and then this was B
Okay.
right here. If you wanted to get here, so you would start with, like, let's just say that was A, and then you would have to go, you can't just go straight to C, right? You'd have
Yeah,
to go
no,
through
you
the-
can. You
can?
can replace. Yeah, these are 2 different rules.
Oh, okay. I
So
thought
this
you
says
had to.
A.
I'm sorry, I thought you had to go with this one first.
No, no, you
I
don't always have
apologize.
to go there. No. Perfect.
Thank you.
No, what he means by that is you have to use a rule on the current leftmost non-terminal in the current
Oh.
string.
Okay.
Oh,
That makes
yes,
sense.
thank you.
You can use any rule you want on that non-terminal, but on that non-terminal. Not
Okay.
non-terminal, but yeah, sorry, non-terminal.
Yeah, so, yeah, leftmost refers only to the substring that I have here, and which of the, doesn't have to do with the rule that I apply, only with which, in other words, not the left or right here, but the left or right just in the string of non-terminals and terminals that I'm building in the derivation. So, yeah, we should do a couple other examples, but here's a rightmost. And I should point out, whether I do a leftmost or rightmost derivation, they'll have the same parse tree. So this would go, S goes to AB. And then I'm going to replace the B first, but it's still going to use the rule that I used down here. So I'm going to have the A goes to BB, and the rightmost is going to get replaced with the D. So that's going to get me A, D, B. And now I've got the left to replace. So that one is going to be replaced with the, here's A, D, B. And again, A, B, B. And then finally, if you replace that A with D, C. So we're going to get the same A, C, D, B. We use all the same rules, we just applied them in a different order. And let's see, where's my... off the end over there. Let's see, here's where I am. Let's see, is anybody tuned in? That is also here. Say again, please.
What's on the board right now is kind of framed perfect.
Okay, okay.
Like that, and I guess.
So let me add a parse tree for that. Just so the parse, the derivation. These are derivations. Show the sequence of rules that were applied, whereas the parse tree just shows the rules and doesn't tell you what order they were. You could apply them. I could do just this is a leftmost, this is a rightmost. I could just do anything I want. So there's something predictable about doing it leftmost or rightmost, right? But I could, this time I could substitute the left one. Next time I could just do the right one. I could switch back and forth, whatever. So it's just for a sense of an orderly way to follow the derivation that we do either leftmost or rightmost. So what does a parse tree look like? The parse tree always starts with the start symbol, which is by convention, we usually make it just an S for like sentence or start. And then each rule is, each character, each symbol that we have in the rule is the child of the non-terminal above it. So what would be the children of S to start? Just so a little bit of experience says separate them a little bit so you can fit other stuff underneath, right? But we usually try to draw them so that the final string is the leaves. That will always be the case, but we try to put the leaves kind of across in a line so it's easy to read, easy to see what we're trying to show here. So the substitutions I can follow here. I substitute that A for AA. So I'll bring A. Those are the two children of that guy. He's going to have A, right? And then his child is going to take the second rule. A goes to C directly. So, and then on the B side, we did one instance of the B, little b, and that other one to get the 5 characters we did direct B. Okay, do one with, here's your challenge, and you do a parse tree for this string. Draw a parse tree for that. So on an exam, I'm going to try to not give something that's too crazy challenging, right? Try to be reasonable. So I'd say this is pretty straightforward. This is a pretty easy one. So this try to make something not harder than this. It's always going to, right, the second row, second level of this tree is always going to be this because there's only one rule. Get the C, that just goes directly off of the A. So the rest of this has to be built from the B side. We know that this B can be substituted with the, now if we do this, what happens next? Yeah, this was probably an unfortunate choice, right? Because if I substitute that B like so, then I can't get any more characters. So I have to do my substitution to put, I want to take the other option, which is this B gets replaced by a B and a little b. Similarly, if I have to add a B, then I have a little b, and I have to also add a big B. So this one is going to lead to that. And then this B can do the B like so. So the sequence makes all the difference, right? I mean, not the sequence, the choice of rules that you apply make all the difference in what you can derive from that language. CDBB, we got there. Okay, I guess I will stop here and go over. Let's see. Lots of outcry of questions. So I will, for the time being, switch over to the exam 2 samples. So here's some, I am now looking at the, let's see, should I put that on, should I share my screen? Let's see. Yeah, let me share the screen, and it's recording, so we'll start there, and if I put something on the board, I'll switch. Okay. So if a DFA has, so here's one of the problems I wrote down. If a DFA has 3 states and accepts a string of length 5, what can you conclude about whether the language is finite or not? What do you know? Has to be infinite because some repetition happened. If you can do one repetition, you can do as many as you want. So that's conclusion. If a DFA accepts a string longer than its number of states, is the language infinite or finite? Has to be infinite. Right? It means it went through at least one repetition. Can an NFA be implemented on a PDA? Yep, we kind of just showed that. All you have to do is replace the stack, or for the stack section of the transition, just make it an epsilon goes arrow epsilon, and it ignores the stack. Is it possible that some language accepted by a PDA could also be accepted by a DFA or NFA? Well, yeah. I mean, we just said that. The regular languages could all be accepted by a PDA. You could build a PDA to accept them. Even though the PDA could do more in that it could do any context-free language as well. Conditions for accepting, right? Those are using up the string, no more string characters left. In an accept state, empty stack. Non-deterministic, more powerful than a deterministic. It turns out that it is, unlike the, this is one of the statements in the text. Non-deterministic actually has more capability because it can try all the possibilities. They go into at some length in proving that, but you just need to know, unlike the NFA and DFA, which have the same computing power, except exactly the same category of languages, PDA, a non-deterministic PDA, accepts a different class of languages than a deterministic one. Can every regular expression be expressed using a context-free grammar? Yeah. What about the other way around? Can every context-free grammar be expressed as a regular expression? No, right? It's the subset thing that we just want to keep that clear in your mind. Write a CFG to implement a given regular language. So if we can do the basic steps of concatenation, closure, concatenation, union, and star. Concatenation is just right, concatenate whatever part, we make that a regular expression, that a regular expression. So this is just a thumbnail guide. If I were going to convert a regular expression to a CFG, I could do concatenation by doing a rule like that. I can do union. A goes to B or A goes to C. So that gives the choice of two different rules. Yes, just like I said I would. Thank you for the reminder. Feel free when I'm messing something up. Turn on the camera. There we go. Yeah. Star is just be complete. So using those are just basic patterns, right? So you can, if you wanted to do, convert, say, any number of A's or B's followed by a B, B, and A star, say. Okay. So what are the things that we're applying here? The basic, these are the basic operations or the building blocks to put together pieces of a regular expression. So here, where are we concatenating? Well, we could, we're concatenating that thing with that thing, with that thing, with that thing. So we can simply just go, S goes to A, B, C. And then each one of these little pieces actually, yeah, we could simplify, but if you're just looking for a way to put pieces together, the A is any number of A's or B's, including 0. So that just looks like what? My rule is A goes to A, A. Alternatively, that's what the union means. I have multiple rules that I could apply. You can generate a lowercase b as many times as you want, or you can just do an empty string. Okay. Makes sense? What does my b look like? I could have not even used a non-terminal there. It's just b just goes to bb. So you could technically just put little b there, because there's nothing much added. And then C just goes to little a, C, or so on. And so that would convert this regular expression to the context-free grammar, like so. Okay, trick questions. Is this a context-free language? Go with that gut feeling. Yes. Is it a regular language? Yeah. Is this a context-free grammar? Yeah. So if this is a context-free grammar, then this probably, and this represents that, then that probably has to be a context-free language as well. Remembering that every regular language is also a context-free language. But context-free languages are a superset. There's more of them than just regular languages. Yeah. Say it again.
It doesn't look like any is added to the context-free language.
Oh, this is an or. This is
Oh.
union. I'm sorry. That is the union operator. Yeah, good point. These all mean. I'll try to. I will be consistent, but this is the same as this is the same as this. Just different notation, but I'll strive to use an obvious one throughout. And so I guess probably the easiest one to recognize as union is this, right? So we'll make them all show that. Okay. Back to our sample questions. Okay, that was write a CFG to implement a given regular language. Given a CFG, show the leftmost and rightmost derivations. We just did that. Given our standard three-state PDA, this gives actually the full answer here below. Mapping the rules to the transitions first. Let's see, given CFG rules below and transitions to the three-state PDA. So we talked at some length about the oops, it ended up with an extra, in my preview, there's an extra blank page. Sorry about that. So the three-state PDA, those, I'm going to give you that. Any question regarding CFG to PDA? So two things you should know is how to make the PDA. So I would give you, once it needs epsilon to push on $sign and start symbol. And then here's where you need to put transitions, and here's where it goes to on an epsilon move. If the $sign is on top, pop it off. Oops. There we go. Step that. Now the transition looks correct. Oh, I guess we can do, let's see. Oh, let's just fill in the, we'll just use this nice little CFG and take a so here's the transitions that would go there, right? Remember, it's non-deterministic, so you should be able to, it will find a path that it exists. So if it goes down a path and it gets stuck because it picked the wrong rule over here, then it'll just back up and try the other rule, and it'll do that, right, to try every single combination automatically. So because we're hopefully a little smarter than the PDA, we can anticipate and we'll trace through a valid string and make sure that we can see how the stack would change. So this is a live example of a different example from what I gave you in the sample question. So you have yet another example. So see if we can cruise through this. We will have opportunity. I'm going to cover new material on Monday. Exam is on Wednesday. But if you have anything that comes up over the weekend, I'll allocate at least to answer any direct questions that you have. I'm not going to try to cover or do review, but if you have a specific question, I will go over those on Monday. So what do we need here? Can anybody see what we need? Well, all the non-terminal transitions that we put here are going to be epsilon moves, and because they're not going to consume input, right? Why? Because the non-terminals are not going to be in my input string. Only Those non-terminals are just for guiding me through the CFG. So it's going to be an epsilon. If I see S on top of the stack, I'm going to replace it. And I have to be careful here with putting it onto the stack in such a way that the left-hand thing is on top of the stack. So that matches. That's the right way to do that. We have another rule. If I see an epsilon and there's an A, and no, so I don't care, epsilon moves, right? If I see an A on top of the stack, I can replace it with little a, big A. If I see an A, I can replace it with, so it's going to try all the, oops, yeah, no, A, and on epsilon. If I see an A on top, I can just pop it off. So how does the thing figure out which one? We don't care, it's just going to pick the right one, or it's going to try all of them. However it does, if there exists a way to get to the acceptance, it'll do it. What have we got left? There's one more, two more non-terminal. Epsilon, if I see a B on top of the stack, then I'm going to replace it with little b's. Epsilon C, I'm going to replace that with the little a, or just pop it off. Okay, so what are the tricky things? I guess make sure you flip left, right, so at the top of the stack it's the left-hand thing. Don't be concerned that you have more than one rule and you can't figure out which one to take on an epsilon move. The non-deterministic nature of the PDA is going to do that for you. And then finally, for each terminal, there's only two of them, A and B. I just need a, on A, if I see A on top of the stack, pop it off. I see a B, and there's a B on top of the stack, pop it off. That, what was the whole point of this? Remember, the whole reason for doing this, where we could easily convert a nice little CFG into a PDA, was that we don't have to try and figure out a fancy method like the PDAs that we see in the book, the couple of examples. You have to push all the ones on, and then, or if it's 0, 1, 0, n, 1 to the n, push all the zeros on and then pop them off when you see ones. It takes a little insight to do that. If you do it this way, then it'll just take care of itself, and you'll get a working, you always get a working PDA if you can start with a CFG. And let's just trace the parsing of, let's see, well, let's see, what's a string that is in this language? I want a really long one. Okay, so I would encourage you to trace how that string would be, oh, it's making it even shorter. Trace how that string would be parsed using that PDA. So the stack, how do I show the table? Got the stack, the input, and the transition. Let's just do the stack and input. Stack starts out with a $S. The input starts with A, B, B, A. Then you got What do we want to do? We want to replace S. It's going to be replaced with CBA. Input stays the same. A is on top. We're going to replace that with a little a. We're going to match. Input remains the same. Now we match the input. Got CBA on here. Used up to A, so we got this. We follow in. This A is going to come off so that we can get the BB. So CB is left with BBA. This B gets replaced with a BB. Then we can match one at a time. So we can fit it. B, B, A. Match those two. We're left with a C and an A. I'll let you get to the end. We just push, the C gets replaced with an AC. Then we match the A's and finally replace the C with an empty. So that's the processing. All right, we'll stop there. Thanks for your patience. Hopefully that will be useful to you. We've gone through all the questions.